Okay, so guys, hey, before we get started today, rather than show you a calendar, what I actually wanted to show you was the folder on my laptop from where all of this information that we're going over in this unit is coming from. I think you probably understand enough about education to know that we as teachers take something as large and unwieldy as chemistry, and we break it down into units. All teachers do this. You take your content and break that down into units, and then those units are broken into days. Well, guys, this is the next unit that we're going to get into. You'll notice by the title that it is a multi-chapter unit. It's 10, 11, and 13. But guys, notice how many days. Yeah, this is the largest unit that we will do this year. This thing is gigantic. We may get in the test before the end of the quarter, which is after Christmas. I haven't really laid it out yet. We'll see. But guys, this is a big unit. And frankly, I'll just be upfront with you. This is by far the hardest unit to teach. This is not the hardest unit. We're going to get into, when we get into equilibrium and acids and bases and kinetics and electrochem, because that's way harder material. This, though, is the hardest stuff to teach. And the reason is because it's hard to get you guys to that point where you appreciate just how hard this is. So guys, what you're going to see is throughout this unit, we're really just going to stop and we're going to go, guys, think about what that really means. Because to really dig into this, guys, frankly, what you've got to do is you've just got to engage deeply in the homework. So as we're going over this stuff in class for this entire unit, there are going to be moments where we're just going to stop and go, guys, picture what you just said, like Avogadro's principle today. We're going to talk about that, and you're going to go, oh yeah, that makes sense. I got no problem with that. But guys, the problem is if you don't drink deeply of it, when you get into the homework, you're going to be answering these questions wrong because you fundamentally don't understand what these gases are doing. Now here's the mistake you're going to make. You're going to answer the question wrong. You're going to pull the answer off the website. You're going to look at the right answer, just replace your answer and skip along without really addressing your misunderstandings of the concepts. So guys, all of this is just a big blanket warning to say, go slow, drink deeply, and when you run into things, guys, that you are not understanding, either because you know you're not understanding or because you're getting homework questions wrong, guys, don't gloss over those. And here's why. The AP authors are masters at revealing your misunderstandings in this material when you get to the AP test. Guys, these are the questions that actually have historically the lowest scores on average of any of the questions on the test. Because when they start asking you questions about intermolecular forces, guys, this goes in all sorts of directions. Because if you don't understand intermolecular forces, that can track back to misunderstandings with molecular structures, with polarities, with what gases are doing. I mean, they can ask you one question and they can lay bare 4 or 5 different misconceptions. So guys, all of that to say, go slow and dig in deep, because you're going to find this gets a little crazy. So guys, we're going to start in chapter 10 today. Everything that we're going to do today is review. So really, guys, this is up to you. If this takes us 15 minutes, so be it. If this takes us an hour and 15 minutes, that's bad because I don't want to stay during lunch. But guys, seriously, this can be as much as you need, or this can just be, oh my gosh, I remember absolute zero, Boyle's law, Charles' law, Avogadro's principle, and Pivner. Because that's what we're doing today. Guys, all of this I just stole out of last year's lecture notes. And so every single bit of this is review. So you tell me. So all of this, guys, is about ideal gases and the gas laws. So if you want the date today, it's the 23rd. And again, guys, seriously, this is as much or as little as you need. So ask questions. Or don't. Are any of you traveling for Thanksgiving? You seen the storm that may be coming? Although Wednesday? We'll see. Okay, guys, here we go. Hey, so the big picture here, gang, is that as we talk about gases, and we'll talk about ideal gases in a minute, guys, it's important that we start here. And again, I lifted this right out of our notes from last time. But guys, we're going to talk about gases. We'll move backwards into liquids and solids as we get deeper into this unit. But we're going to start by talking about gases. So guys, fundamentally, what we're going to do over this unit is we're going to develop for you a mental picture of what gases look like and what they're doing. Now guys, here's the trick. This is the way that I've taught this unit since I started teaching AP about 15 years ago. Finally, the AP curriculum is caught up with me, and now they're actually having you draw these pictures on the test. So it's going to be all the more important that as we go through this, you are developing not only a good mental picture of what gases are doing, but it has to actually be a video rather than a picture. Because guys, you understand that none of these are static, that these things are moving along progressively throughout the unit. I will bring in simulations and animations that are showing you what gases are doing. But guys, fundamentally, we've got to understand that gases look something like this. So you tell me, guys, what do you know to be fundamentally true about gases? What do they do? Why do they do it? Lay it on me. What do you got going on in your mental pictures? Say it again. Yeah, so gases are all spread out. Guys, why do gases all spread out? No intermolecular forces. So now let's track that backwards. What is it about the particles that makes it so they don't have intermolecular forces? They're, well, not just speed. They are moving quickly. Say it again. That's true, and that allows them to spread out. But guys, take, for example, natural gas, right? Methane, Bunsen burner gas, or oxygen or nitrogen, or all of those things that we know to be gases. Even at room temperature, they have enough energy to spread out. So what has to be true of the particles? Nonpolar. Remember, guys, the particles that tend to be gases, especially at room temperature, are the nonpolar gases or the nonpolar molecules. Because they're nonpolar, that means they don't exhibit very strong intermolecular forces, and that allows them to overcome those intermolecular forces. And as Vanessa said, they spread out as gases. Now, guys, does that mean that they are not polar at all? No, and you're going to find out, guys, that every single substance on this planet can be liquefied. What does that mean? It has to develop, or it has to exhibit some sort of polarity. Guys, every substance on this planet, including the least polar of all molecules, which is diatomic hydrogen, even that can be liquefied. So guys, all substances, even if they seem to be perfectly symmetrical, all substances can be liquefied, meaning that even the most symmetrical of substances can still exhibit some polarity. And we'll talk more about that as we go. Okay, so now we understand that these things spread out. So as a result, what do gases do when they're contained within a vessel? Do you remember? They take on the shape and the volume of their containers. So they spread out. And guys, this is going to be important in homework even today, that we understand that the volume of the vessel is equal to the volume of the gas because they spread out to fill the volume completely. You guys okay? Anything else to add to our understandings of gases? Yeah? So you have to be careful with that, because It does, you're right. So carbon monoxide is more, or maybe a better example would be carbon dioxide, right? Because in Utah County, we've all made root beer, right? So you got the big orange cooler, and you put in the water, and you put in the root beer extract, and you put in way more sugar than you ever thought could get dissolved in water, right? And then you put in the dry ice, and you see the dry ice, right? The carbon dioxide, you guys all know what I'm talking about, and it pours over the edge of the cooler, and it covers the table and it covers the floor. Carbon dioxide is more dense than air, and so is carbon monoxide, but that doesn't mean there isn't any carbon monoxide up here. It does spread to fill the container, it just doesn't do it equally. So there is still some up here, but there's still a density gradient based upon the density of the substance. So yeah, is that okay? Yeah. Yeah, that's funny stuff, right? I don't know if you've seen the videos of a big old aquarium full of sulfur hexafluoride, and you can actually get an aluminum foil boat to float on it. Have you seen those videos? Yeah, same thing. You're right that because it's more dense, the majority of it will be contained within that aquarium, the videos I've seen. But there is still some spread throughout the room. Yeah, okay. You guys good? Yep, good. It's about 80% nitrogen. Yeah. So, yeah, it's nitrogen, carbon dioxide, oxygen, of course, trace gases. Do they all know? And it's interesting, you guys' brains are starting. That's going to be one of the hardest things to get our brains around. We're going to, right after Thanksgiving break, talk about something called Dalton's Law of Partial Pressures. And what you find out is that counterintuitively, although it seems really simple, when you get mixtures of gases, each of the individual components in a mixture of gases behaves as if the other gases aren't there. So they can have their own densities. But even if you do have a mixture of gases, each of those gases behaves as if their volume is the full volume of the container. So, and we'll talk about that more. I'm glad that you're thinking about it, because it's more difficult to think about than it initially seems like it would be. So, you guys okay with all of these thoughts? Okay, and we're okay with the idea that things that tend to be gases are also the things that are nonpolar. We good? Okay. So guys, with that said then, we now need to talk about this idea of ideal gases. What do you remember? First of all, they're not real. But guys, as I told you last year, or maybe whoever you had for chemistry, guys, just because ideal gases aren't real, it doesn't mean they're not important. And this is not us dumbing things down because we're just AP students, and when you get into college, you'll actually find out that, oh, this is just a game you play in high school because you're not smart enough to do it right. Guys, ideal gases are a very important way of thinking about gases, and they're nice because it simplifies the math, but they're a very good approximation of what gases actually do. So guys, do you remember the two things that make a gas ideal that actually are not true of gases? Do you remember? They do have mass, but no volume and no intermolecular. Here, let's just get them up here. So guys, I don't know that you need to write this down. This was sort of the explanation of why we do it and why we use this simplified model. But guys, it goes like this. When we talk about ideal gases, you may want to include this in your notes. And we can talk more in depth about why this is so important and yet counterintuitive. So guys, ideal gases are composed of molecules. And I would encourage you to underline that word molecules. You know what? I don't even like molecules. Let's use particles. We can use that term in here. It's actually the correct term. So guys, when we talk about ideal gases, these are gases that are composed of particles and particles could be atoms or molecules, particles that have mass but no volume. So guys, what does that mean in layman's terms? What does it mean that they have mass? Well, they weigh something, but what does that fundamentally mean? They're there, right? They exist. They contain matter, so they are there. But what does it mean that they have no volume? They don't take up space. And guys, that's obviously impossible. If something's there, it has to take up space. But guys, the thing that's nice is if we pretend like these molecules don't take up space, then all of a sudden the math becomes a lot easier. Now guys, did you get that down? You're okay? You're good? Okay, now let me go back and ask you, and this is a question that you've never been confronted with before. Guys, given this as our model for a gas, why would it be appropriate to say that these molecules are there but don't take up space? Compared to what? And this is comparative. They're so small compared to the overall volume. So guys, the idea is this, and maybe what we should do is delete a few more of these particles. But guys, the idea is that these molecules are so small compared to the overall volume of the gas that the volume of the particles themselves is insignificant. And in your notes, I would encourage you to write down that word. That's your money term when you explain this to the AP graders. Guys, the word you want to use is insignificant. So the volume of the molecules themselves is insignificant compared to the overall volume of the gas. So these molecules could be bigger or smaller, and it doesn't really have a bearing on the volume of the gas because there's so much empty space around the molecules themselves. Because the analogy, which is really fitting right now, is this. So imagine if we measured your volume in liters, okay? And then imagine you guys go home over Thanksgiving break and you all just chow down and don't exercise, right? The perfect way to spend Thanksgiving. 5 days later, you have gained a bunch of weight, which means you're now physically bigger, your clothes don't really fit anymore, and you come back after 5 days and physically your bodies are larger. Does that mean we need to build a bigger school? Why? You're all bigger. It's insignificant compared to the space in the school, right? You guys could get bigger and smaller quite a bit, and it doesn't change the size of the vessel. It's funny to think of schools as vessels that hold students, but it doesn't change the size of the vessel because you have a lot of free space around you, and your volume is insignificant compared to the volume of the school. Well, guys, similarly, these molecules can get bigger and smaller, but because their volume is insignificant compared to the volume of the container, we can pretend like they have no volume at all. Do you get the idea? Okay, so that was oversimplification number one. Now, guys, and there's the term, if you want to include it, the term insignificant. Now, do you remember the second simplification? No intermolecular forces. Now, guys, I fear to do this because I don't want you to think that intermolecular forces are magnetism, but the analogy holds true. So, guys, here we've got a couple magnets that are attracted to each other. If I do this, are they still magnetic? Sure, but why aren't they attracted to each other? They actually still are. But those forces of attraction are so weak over these distances that they fundamentally have no influence over the molecules themselves. Now, guys, if you go back to your mental image of a gas, these molecules, all of them, as we said, are at least somewhat polar. Maybe not very polar, but polar enough that if we bring them close enough together, we can get them to liquefy, which means they stick. So why is it that we can say that these gases have no intermolecular forces? Because over the distances between the particles, fundamentally those forces are so weak that they really don't influence the behavior of the gas. Is that okay? Okay. So guys, again, the gas particles are so spread out that they actually behave as if they can't attract each other. Now guys, later on in the unit, what we're going to do is we are going to talk about the conditions where gases behave ideally and where gases behave non-ideally, which we call behaving like a real gas instead of an ideal gas. But I'll bet we can kind of talk about it right now in order to sort of prime the pump. So guys, what do both of these characteristics of ideal gases have in common? You can just read the sentences and find it. So spread out, right? Guys, the reason that gases behave ideally is because they're so spread out. So under what conditions would they not behave ideally? When they're not spread out, when they come together. And guys, when they come together, they don't behave ideally. And Caleb, that's one of them. High pressures will cause them to behave non-ideally. And what else? Really low temperatures, because in either case they come closer together and then they behave non-ideally. You get the idea? Okay. So guys, that was sort of the refresher on ideal gases. You guys good? Okay. What about this? Do we need to talk about standard temperature and pressure? Let's just do it really quickly. And 20 Celsius. So guys, when we talk about standard temperature and pressure, 0 Celsius. When we talk about standard temperature and pressure, that is 0 Celsius or 273 Kelvin. And guys, if you don't remember, the conversion between Kelvin and Celsius, well, Celsius and Kelvin is at 273. Do we need to go back over the Kelvin scale? Remember when we did this last year? I won't even flesh it out if we don't need to. Where remember the idea that in Celsius, the 0 point is the freezing point of water. In Kelvin, the 0 point is absolute zero. And in either case, Celsius and Kelvin degrees are the same size. So do you remember this? Should I scratch this in really quick or no? You're okay? Okay. So Celsius and Kelvin. And then, guys, standard pressure is the pressure at sea level on an average day, which is 14.7 psi. You don't need to know that. But then that is equivalent to 760 millimeters of mercury, which is torr, or 1 atmosphere. Yeah? Just data over... Yeah, it's literally just data collected over the centuries, decades at least. Wherever you're at sea level, yeah. And so they've just taken the average, and they don't do that anymore. Now they have it's defined as this, but originally it was just defined as an average day. So yeah, you okay? Okay. So guys, these are actually then the units that you need to know. 760 millimeters of mercury or torr, 1 atmosphere of pressure, and then 101.3 kilopascals. All of those are equivalent, and then depending upon the setting, those are the ones that you need to know. We are almost done. You guys good? Can I go? Okay. So guys, moving along then, we come to the laws that govern the way that these things behave. You may remember Charles' law, Boyle's law, and then the ideal gas law. So for those of you that don't remember, Charles' law is the direct relationship between temperature and volume. And so guys, the thought then simply becomes this: if the temperature goes up, gases become bigger. If the temperature goes down, gases become smaller, assuming that the pressure is not changing. Now guys, maybe we can talk now kinetically about why that is true. Why would gases get bigger when you heat them? They're moving faster, they have more energy, and they move outwards. And then similarly, when they cool down, they slow down and they move closer together, and the volume goes down. Is that okay? You're okay with the idea? Okay. So guys, we talked last year about the idea that this is why your tires look flat. Remember that? And I don't know if you guys have had this experience, but you go out in the morning, it was 20 degrees this morning, right? Fahrenheit, which is below 0 Celsius. And guys, you go out and your tires look flat. But in fact, there's the same amount of air in there. They only look flat because the gas is cooled and it's contracted. And then similarly, but the opposite, did you remember talking about this? That's how hot air balloons work. You remember the idea? That there is in fact a big trap door. Remember this? Yeah, there's a trap door in the lid of a hot air balloon, and when you heat up the gas, it expands, but instead of the balloon getting bigger, they open a trap door and those hot gas molecules escape, and then when they close it, the gas that's still contained in that envelope has a lower density, and the lower density gas on the inside floats in the higher density gas around the outside. Did you? Really? And you saw the trap door and all of that? And, yeah. Cool. Oh my gosh, absolutely. Yeah, it's pretty cool. Nice. You guys good on Charles' law? Okay, then guys, sort of the other side of this coin is Boyle's law, which says that the volume of a gas varies inversely with pressure. So we gave these examples that as pressure goes up, then the volume goes down. I think about it as giving the gas a big old squeeze. And as you squeeze something, more pressure, it gets smaller. And then conversely, if you let off the squeeze, the volume goes up. And guys, last year we talked about these examples. We talked about why they launch weather balloons. Did you guys talk about this in Miller's class? That when they launch weather balloons, this is actually what they look like. This is a fully inflated weather balloon before they send it up. And what they do is they send this balloon up to the very edge of our atmosphere. These things get up there 30, 40,000 feet. It's pretty crazy. But you'll notice that this thing is horribly underinflated. What would happen to a weather balloon if they sent it up fully inflated? It would quickly pop, right? Because as you go up, the pressure goes down and the volume gets bigger. And as that happens, the balloon would expand and it would quickly fail. So when they send these things up, they actually do them. That'd be fun to do. We could actually do the math and figure out the percent that it would grow given the pressure up there. And so they send these things up with just enough gas so that they're fully inflated at altitude so that they can hover up there and collect weather data. Yeah. I would think so. Well, it used to be really plentiful. Now we're actually in a helium shortage. Yeah, I don't know if you guys, have you heard about this? That they actually take these old abandoned mines and our government even is stockpiling helium inside of these mines. And as low temperature physics and chemistry is becoming more prevalent, I mean, so many like MRI and CT and PET scans and all these medical processes and all this stuff in physics is actually requiring liquid helium to work. And we're actually running out of liquid helium. And so consequently, are they still doing that where they ration it, where you try to go get a dozen balloons for somebody's birthday and they won't sell them to you? Have you guys tried? I don't even know. Are they still rationing it? I don't even know. But yeah, it's... My understanding, though, is that they can do that, but my understanding is that for commercial uses, rather than make it, they just condense it out of the atmosphere. I'm not sure, but I do know we're running out. And then, guys, we looked at this idea, too, that as you go down, the volume decreases. And the thought being, as you go down under the surface of the water, there's greater pressure under there. And notice, guys, that the relationship is linear, that if you have a volume of air with a volume of 1 at sea level, when you go down 10 meters, you actually double the pressure, and the volume is cut in half. So every doubling of pressure will have a proportional decrease in the volume. And if you do that long enough, eventually the gas will liquefy by pushing it together tightly enough. You guys good on Boyle's law? Charles and Boyle's? We're good? Okay. And so guys, then what we did is we talked about how this comes together mathematically with this equation. Now guys, this is not on the AP equation sheet, I don't think, is it? But even if it's not, they expect you to be able to solve it, which seems a little weird to me, but that's what they've done. It's not there. But guys, it simply says that the pressure times the volume divided by the temperature of one gas is equal to the pressure and the volume divided by the temperature of that same gas at a second set of conditions. So I sort of misspoke. It's not one gas and a second gas. It's the same gas responding to change. And so given this equation, you can take the initial conditions of a gas and then figure out things about it at a second set of conditions. So this is the equation that brings together both Boyle's law and Charles' law. The reason that they expect you to be able to understand this is because you know that temperature is a direct relationship to volume and pressure is an inverse relationship to volume. And because of that, you can piece the equation together just by sort of thinking through it. You guys good on that one? And you'll have some of these to solve in homework. You okay? Okay, so guys, let's do this then, and then we're done. Avogadro's principle. Now guys, I suspect that you're probably okay with Avogadro's principle. I would like to spend the time to make sure that you're all okay with it, but let's sort of throw this out here and make sure that you're good. It's sort of the beginning of the difficult conceptual stuff as it applies to gases. So if you remember last year, I asked you this question up on the board, and I said, imagine that you've got a 30-gallon trash can. And if you've got a 30-gallon trash can like this one up here, and then imagine that we were going to try to fill that trash can. So imagine that we were to try to fill my trash can with tennis balls. You can kind of picture that, right? You can sort of picture this trash can all full of tennis balls. And then imagine that we took the tennis balls out and then we went back and we filled the same trash can with volleyballs. And then we asked the question, which one would require more? Would it take more tennis or volleyballs to fill the can? And of course the answer is, of course the answer is tennis balls, right? So the idea is that it takes more small things to fill a space than big things. Remember when we thought through this? And then guys, we came back and we talked about the counterintuitive nature of what happens with gases, because Avogadro said this, that if we have two similar samples of a gas, and by similar we mean same temperature, same pressure, and same volume, it will actually contain the same number of particles. And guys, you may remember this. We talked about the difference between this and this. Remember the idea? That if in fact, and we're allowing these airsoft BBs and these ping pong balls to represent gas particles, if it was in fact this inside of a balloon or whatever, a vessel of gas, then in fact it would take more small gas particles to fill a space than large gas particles. But then guys, we had sort of that aha moment where we realized that there's so much free space around these gas particles that the gas particles could be very, very small, represented by these airsoft, and then they could be bigger as represented by ping pong balls. But if these two samples of gas have the same temperature, pressure, and volume, there will be exactly the same number of particles in there. And again, guys, remember our magic word is insignificant. The differences in gas, the size of the molecules is insignificant compared to the space they occupy, and therefore Avogadro's principle is true, and they have the same number of particles. Do you remember that? Is that okay? So we sort of summarized it like this. And we said that we can then represent this mathematically using what is PIV-NERT. And guys, PIV-NERT is the mathematical representation of the ideal gas law that says if you know that, well, you can have a relationship between the pressure and volume, the number of moles, and the temperature of a gas, and it's all related by this universal gas constant, which is R. And guys, on the, well, you may as well grab it if you want to look this up on your equation sheet. They do give you the PIV-NERT equation, and they give you several different values for R. You may want to take a look at them and make sure they're comfortable for you. So you'll notice that on the equation sheet, they do give, does anybody need one, by the way? You do? Okay. You guys all okay? Oh gosh, sorry. Yep. Anyone else need one? You're good? Okay. So guys, you'll notice that on the equation sheet on this side, this says gases, liquids, and solutions, which by the way is everything we're doing in chapter 10, 11, and 13. They give you PIV-NERT, but then over on the right-hand side, they give us multiple different units for R. The one that we're talking about here that relates liters and moles and pressure is the 0.08206. But notice, guys, that when we use that value, our volumes have got to be in liters, our amounts of gas have got to be in moles, and then our temperatures have got to be in Kelvin. You guys good? So guys, what about Avogadro's principle? Are you okay with that conceptually? Again, the idea that small gas molecules and big gas molecules doesn't matter, same number of molecules in any given sample if their pressure, temperature, and volume is the same.
So, even though there's limits for each, then suppose if those reaction gases,
Yeah. By air, do you mean empty space, or do you really mean air? Right, right. So say that again. You mean empty space, though.
In an actual gas instead of big molecules.
Okay.
The difference in those sizes.
Right.
Not gonna make a difference.
Exactly. Yeah. So and actually yes, the pressure. So long as, and this is where this all starts to multiply on itself, because pressure is a function of how hard those things are hitting the wall, right? And the pressures would be the same if the temperatures are the same. But what you're going to find out later is if the temperatures are the same, their speeds will not be the same. The smaller particles are moving faster, slower, so they have the same kinetic energy. They'll be exerting the same pressure. Yes. Yes, they will have the same momentum but different speeds because they have, and that gets back to kinetic energy, which is where we're headed with this. So, yeah, again, no, it's a function of kinetic energy because pressure is force divided by area. And so force is a function of really both, but it's a function of speed. So it's how hard, and it's also a function of frequency. So, but that's also a function of speed. Correct, exactly, yep. You guys good? Okay, so guys, we have half an hour. This is what I'm thinking. I wrestle with this because, you know, we have 3 big holidays, right? We have Thanksgiving, we have Christmas, we have spring break. Typically, what I like to do is not mess with Thanksgiving. Christmas, I usually evaluate and see where we're at. And then every year, guys, Thanksgiving, you're going to have things to do over break. But Thanksgiving, as much as I can, I try to isolate it and just let it be family time because it's short and it's, anyway. So guys, my intention here in giving you 30 minutes is that you get your homework done and then you don't have homework over Thanksgiving. So let's spend this half an hour. Let me give you your homework. and we'll go from there.